Hello, my name is Kamil Owczarek, and I'm a big data Scala/Akka developer at Quintiles IMS, which is, broadly speaking, a company that deals with big data in the medical sector. But I won't talk much about it since that's not what we're here for. What we are here for is to talk about the relatively new module in the Akka toolkit, Akka Typed, and how it changes the way that we will be thinking about actors in the future. Now, how we're going to do that is I'm going to start a little bit about talking about the origins of actors and how they were originally intended to work, because that will come into play a lot later. Then for those of you that are not Akka developers, have not used Akka, I will make a really short introduction to Akka. By the way, who's never used Akka in here? Quite a few people. So that will be for you. And then I will do a similar thing, so make a introductory actor in Akka Typed, so you can see at the basic level what the difference in philosophy is, from which I'll proceed to talking about the core of Akka Typed, which are behaviors, typed behaviors, and that will be the, let's say, most complex part here. From where I will go to telling how Akka Typed actually helps us solve some small problems that we have observed while working with Akka for many years. And I'll say a bit about what the future holds for Akka Typed as a component of Akka. Short summary, and we're good to go. Just one more thing. So the presentation will be fairly technical, and I will be showing a lot of code here. You can find the code samples on my GitHub under GeeCON Akka Typed, and they're all in Scala because I'm a Scala developer in my day job. However, I might do Java samples in the future, and they're all developed with the extremely latest bleeding edge API for Akka Typed. Yeah. So about the origins of actors. Actors have actually, they are a fairly old concept, comes to think about it. So the first time they were actually introduced, it is said to be in the paper by Carl Hewitt, Peter Bishop, and Richard Steger, a universal modular actor formalism for artificial intelligence, which was published in 1973. So yeah, that's pretty old. And even the implementations, first implementations got really old by now. I mean, Erlang had actors back in 1986, so it's over 30 years old right now. And the idea behind actors presented in that paper was basically that actor is an entity that starts working when it receives a message, an immutable message in that case, and when received that message, it can essentially do one of the three things. Send some messages to some other actors to which it has references, creating child actors for itself with which it can also interact, and designating its own future behavior. So if you think about it, for instance, like a very simple thing, like let's say a light bulb, right? If you imagine it as an actor, it's actually a good exercise for modeling actor system, imagining real life stuff as actors. What a light bulb does is it receives electrical current, right? And it emits photons, so light, basically. So receives message, sends message. But it may so happen that if you receive the current that will be too high, a light bulb can break, right? It can just burn out. So in that case, we have the third point here, which is basically changing behavior. That after, if the current is too high, the next behavior from now on for the light bulb will be basically do nothing because you burn out. And this model is extremely simple, but it is very good because it can accurately describe almost anything around us. It was actually originally meant for simulations. And if you think about complex systems, sometimes it's really hard to mathematically solve complex systems from the bottom, right? But it is sometimes easier to simulate them and to figure out the solution in that way. So this is the, let's say, great idea behind the simplicity of actors. And the model, as it was originally designed, it caught up for some time, but then the hype kind of winded down. And if you think about, for instance, Java when it originated, and for many years we didn't really have any actors in there, right? But as time went on, we happened upon the times where everything is pretty much running as a parallelized process, multi-core, and sometimes even in cluster, right? So what people started doing specifically in Java, when the need for parallelism arose, they started working with threads. You had the famous Java 5 concurrent API, and while they were doing that, they realized one very important thing. Basically, that multi-threaded programming really sucks. What I mean by that is that when you're doing multi-threaded programming with the threading API, you're likely to invest a lot of work in it, and the outcome may not always be that great. And there are many theories why that is. Myself, I think that the reasons are threefold. First, we don't really think about actions in parallel. So you are writing your code, you're quite likely to actually not take that into consideration and make some mistakes. For instance, sharing mutable state can cause failure in threading. And if you really focus on that, and if you think all the time about threading and you will get all that correct, then you're probably not focusing on what you should be focusing on, like logic, right? Like interactions. That's what programming should be about, not technicalities in the end. So either you make technical mistakes or you make logical mistakes. You might write a very good multi-threaded program which doesn't actually do anything useful, but yeah, it gets all the threading right. And then it doesn't really scale that well, working with threads. If you have a program that goes beyond simple scatter-gather, then if you write it on threads and the number of threads increases by 2, you're pretty much likely to rewrite it, right? So yeah, you know this image, right? It's a pretty famous metaphor of multi-threaded programming, but I guess it's a mild one. In reality, like half of the puppies will probably be dead and like a fourth of them would just run away somewhere for no reason. Well, at least that's my experience here. And because multi-threaded programming sucks, some wise people thought that you might actually make actors may actually make a comeback here. Because if you think about it, actors are really good for what we want to have, which is essentially massive parallelism. Since actors are isolated, they exchange immutable messages. In the model, you don't assume anything in particular about what processes happen in parallel. All of them can happen in parallel, for all we know. And they're generally faster and easier than working with thread-based APIs, while if you program in actors, you tend to focus purely on logic and interactions instead of, technicalities and locks, right? And that's why, I guess, Akka was created and first released in 2009 with the Akka Actors module. So this is what I will refer to as untyped actors here, as opposed to the Akka typed. And now, for those people that haven't seen Akka, there will be like a really short introduction to it, so pay attention. We'll be writing our first actor. This will be like an actor which takes part in a game of ping pong, like a hello world for distributed systems, really. And ping pong, this game, one actor does ping and the other does pong. This one does ping. And what you need to do to program your first actor, you need to have a class, which will extend the actor from standard Akka toolkit. It will implement the receive method, and what this method does is essentially it's a partial function operating on any. So you have to pattern match on the input, and it can be pretty much anything. And then you can do all the actor stuff, sending messages, creating children, printing, apparently. And one other thing that you can see here is the actor ref, which is taken as a parameter, which is basically a reference to another actor, a type of black box reference, meaning that you don't have access to any fields of the other actor. You just can send messages to which is kind of the idea. And when we code that actor, what we need to do is we need to put it in the actor system. So we create the actor system, and then we call actor system actor of on the instances of our actor class, and we get the actor refs here, to which we can then send messages using the exclamation mark, otherwise known as the tell operator. And this is how it works. You can find it in code samples working and doing all the ping pong stuff. And of course, Akka, this is just like the basics of the basics, right? There is way more to Akka, which you can find on the akka.io/docs page that explains actors, all the possible interactions, all the other modules, which over the years emerged on the basis of actors for multiple functionalities needed in modern applications like HTTP, reactive HTTP, reactive streams, creating clusters of actors, remoting, persistence, pretty much all that you need. And of course, we have also the functionalities of supervision and registering child actors as originally intended. Sadly, I cannot go into details on all of this here, but yeah, I really recommend the read if you haven't seen Akka. And now let's proceed to comparing this to how basic actors look in Akka Typed. But before we do that, I need to give you one big warning, which is basically Akka Typed API is still evolving as it's a fairly new module. And actually, since I started writing this presentation, I kind of had to rewrite the code samples 2 times because of all the changes in API. But what is good here is that while the API is changing, the core philosophy of the module, which I hope to explain to you today, does not change. So if you will understand this core philosophy, switching from one API that works in this philosophy to other is actually a matter of minutes. And with that in mind, let's create our first actor. So as you can see straight away, Akka Typed is centered around something which is called a behavior, right? So this is a behavior of the actor on a particular message. And what a behavior does is essentially it is typed, it is parameterized with a type T, and it takes a instance of that type that was sent as a message to it, to the actor, does something, in this case just printing the square of the integer that we're receiving, and then it has to return the behavior of the same actor for the future, right? As I mentioned in the beginning, the original idea of the actors did account for that as one of the 3 core things that an actor can do. So this is an extremely simplistic actor. So what we want to do, if we don't need the behavior to change over time, we just return actor same, which means basically apply the same behavior over and over, right? And then once we define the behavior, it's time to wrap it in an actor. And what we need to understand here is that in comparison to traditional Akka, actor system in Akka Typed is also parameterized by type. So when you have the top of the actor hierarchy, which is called the guardian actor or root, right? In traditional Akka, it was kind of a given, right? It was there and you didn't need to do anything for it to exist. One of the reasons being that it wasn't typed. Here it is typed and you need to insert behavior for the guardian actor yourself. Well, in our very simple case, let's just insert the square behavior that we defined on the last slide. But in the next slide, we'll see more of that, how do you define the guardian for a particular purpose. And just a quick note, if you are mocking something or you don't really need a guardian actor, you can just put actor empty, right? And then once we have the behavior defined, a simple behavior here, once we have the system and we have the reference to it, which is here the actor system parameterized by integer, we can essentially send messages to it using the same tell operator, and it will work. The only twist here is that since the reference to actors are also typed in Akka Typed, right? The only thing that you can actually send using the tell operator here is an integer. If you tried to send any other type of message, this is a compile time error. Well, you might think that's sad, but actually I think this is really good because it basically protects our actors from unwanted interactions. And okay, so for that part, do you more or less all understand how it works? Because I will go into, let's say, deeper territories next. Good? Okay, so let's talk a little more about in terms of behaviors. As I mentioned, they are the core of Akka Typed right now, and they are, of course, parameterized by type. which means that this is the only type they take. And what they give us, apart from, of course, type safety, is a few things. First of all, I guess that everyone who is an Akka dev here knows this kind of situation where you wrote your small single responsibility actor, right? Worked well for some time, but then you had a demo or something, and you had to add functionalities, and it evolved into this like huge mess of an actor that pretty much does everything and nothing at the same time. Anyone does Akka hasn't ever had that experience? Oh, you're a lucky guy actually, but only one person, right? So that's what used to happen in the past. I mean, it's not actually a fault of Akka, it's more of our fault, but that's reality. So here in behaviors, that will because of the strong typing, that will most likely not happen. Behaviors actually, the way they work, they actually force you to do this right. And they also, as you've seen in here, the code I wrote was pretty functional programming. Like, I didn't really define a class, and I didn't really do any kind of vars, as it happened in the past. So in general, you can say that the let me just, okay, sorry. So in general, we can say that it promotes a more functional approach to writing actors, right? Then it is more testable, because when you tried testing the untyped Akka, you had to use Akka test kit to basically pick into your actors, right? You couldn't do that. For instance, if you implement a state machine, which I will do in like 2 slides, you couldn't really verify how the machine changes the states because it was in the black box, yeah, in your var inside the actor. Well, here, if you use behaviors, you basically have a function that in the end returns you the next behavior. So you can check in this way, you can match states to behaviors, and you can basically unit test if the giving the actor an appropriate message returns the appropriate state, triggers appropriate state transition, which is a huge plus in, for instance, finite state machines. And then, last but definitely not least, typed actors seem to be faster than regular actors for a reason. So first behavior I'll talk to you about is the, let's say, stateful behavior. So what we've seen in this, the simplest example was an actor that doesn't change its state. It works, it doesn't change its behavior, it works the same way on every message. But in many cases, as even in the stupid case with the light bulb, right? Well, wasn't really how real objects behave in the reality surrounding us. The actors and the objects may change their behavior, and this is what Stateful is all about. It is a really good tool for finite state machines, so I will use an example of that. And if you think about finite state machines, they have numerous applications in programming, right? From, I don't know, mathematical linguistics to Markov chains in machine learning. We can enumerate a lot of the example how to use them. So let's look at a very simple vending machine behavior. It will have 3 states. First one being idle. It basically stands there and does nothing. Then you can order first, and you will go into the ordered state where it kind of waits for you to give it a money, to make a payment. For the sake of simplicity, I assume that you only can make a correct payment. You cannot make, insufficient payment or something. And if you order and make a payment, it will basically give you the item you need and go back to the idle state for the next customer. You can do it otherwise, first paying, and then it will wait for the order. If you get a timeout and the order doesn't arrive, it will give you back your money. If you make an order in time, it will give you the item you wanted to buy and return to idle. So in Akka, normally, you would kind of do it like this. You would have a mutable variable called state, in which you will have a state of your state machine, right? And you will receive input, sometimes sending the output to the client. So you can see there is a lot of pattern matching here, because you have to pattern match on the input and the state on the same time to return the output. And actually, yeah, so it will look like this. In comparison, if you were to do Akka type, it will look a bit like this, in which you will define, I would define 3 functions, each of which basically is corresponding to a behavior for one particular state. So you have idle state behavior, you have ordered state behavior, you have paid state behavior, and depending on messages, it does reply to the client if needed, and then it designates the behavior for the next step. So you have a neat simulation, and again, if you look at these functions, you could actually run this and check the behaviors, right? So this is fairly testable. And one of the things I would like to for you to notice is that you have the actor ref on the top, which also is parameterized by type, and that's how you will do it in Akka types. All the references are parameterized by type, so it means that if for the references you can only also submit correct type. You can do no wrong in here by design. And next behavior is full. So a quick question, because for 95% Akka typed is, Akka in the original version was exactly like the actor model that I presented in the beginning, the original one. But there is one small difference. Does anyone have an idea? Well, the difference is, it said that actors are only activated on messages, right? But actually, you have methods like pre-start or post-stop in actors, which are not activated. It's a behavior which is not strictly activated on messages, right? You don't receive any message in there, it's just the element of the life cycle. Well, in Akka type, they kind of went towards the original idea in that the events, lifecycle events are also messages that you receive. But of course, you cannot receive them in the core method of the behavior, which is on message, because they're not typed the same. Their type is signal, and you have multiple implementations like pre-start or post-stop. And there is an additional method in behavior, which is called onSignal, in which you can do that if you override it. So this is the full behavior. By full, we mean responding to messages and signals at the same time, right? And signals, of course, can also change the future behavior of an actor. And the other thing that I kind of sneaked in here is, if you look, for instance, here, right? What are the parameters of the methods? Well, there is the command, which is essentially the type of the behavior, but there's also a hidden parameter here, right? The underscore. Any guess what that is? Yeah, it's the actor context here, right? Which is, again, also typed with the same type T. And what you need it for is, for instance, from the core things that actors do, you need it to spawn child actors, right? You essentially do it like, yeah, sorry, it switches a bit slowly. Like here, you can take the context and you can spawn child actors if you need them, right? So this is an example of a kind of behavior where I'm using actor deferred to create when the actor is started, I am spawning child actors and only then defining the target runtime behavior, including the references to these child actors to work with them. And then I have, again, actor immutable with the basic behavior of forwarding messages to child actors. So this, as an example, could be the definition of the behavior of a guardian that is a guardian of a small system. By that I mean, if you have a user which has different parts to it, like, for instance, credentials here, right? Or, I don't know, user contact data. You might have different services that or actors here that operate on these parts. You can have an authentication that would check credentials and say authenticated or not authenticated. And you could also have a contact provider that would select the best way to contact the client, right? And on top of these two, you will have this as a guardian that will bring these actors to life, because you cannot, in Akka type, bring them to life as we used to, like kind of shooting them from the side into the actor system by calling context actor off, right? In Akka type, the guardian, all actors have to be spawned by other actors. So you spawn the actor system with a guardian, then the guardian creates its children who create their own children, and that's how the actor system and the actor hierarchy is defined. And last but not least, something which is a bit lighter for you to think about is the tap behavior, which is essentially, it works like this. If you have an actor, right, with its own behavior, you might want to put something in front of it. So before the actor receives the message or a signal, because you can see there are two functions in here, one for a message and one for a signal, you can basically do something before the message will go to your actual actor. So you can, for instance, print it to console, like here. Or you can ignore it, like the signal here. Yeah, and that's like the set of, let's say, core behaviors. Actually, there are a few more behaviors, but you know, I can't really go through them all right now, so I encourage you to check the code samples where I use that a little bit more. Yes? Well, I mean, I'm not sure if I understand you correctly, but basically the behavior of well, I mean, the command here is, you can see it's actually an instance of user command, right? And what you can see in the bot. Yeah, well, that will help.
Okay, so when the first example with when you were creating system, it was really obvious. You were passing behavior to the actor system. It was typed. It was integer that was allowed to pass. But here you cannot. Okay, you can type it with user command, but it's not the strict typing. It's only you're saying that okay, everything that extends user command will do, but actually it's not the strong typing, right? You can extend your API of the actor with different types that extend to user command, and they will go to the actor, and the actor will accept the object, right?
Well, I mean, it's like that. Yeah, you're kind of right, but this is, let's say, as not a set in stone thing in Akka typed as much as it is just a way I.
But it could be object, right? It could be object, and then while matching, you could just decide if you are able to accept the object or not, right? So here, for this pattern, you are not able to in compile time to decide that you want to have this object or not, this type or not, right?
The thing is here, yeah, in this particular example, yes, but in Akka type, you don't have to do it that way, meaning that it is the guardian that creates the child actors, right? But the messages don't have to pass through the guardian. So you can have strongly typed children of that guardian, and the type of their behavior doesn't have to necessarily extend the behavior of the guardian.
But if the guardian is a proxy, it will be untyped.
Yeah, so I might have did it a bit, awkwardly here by making guardian the proxy, but it doesn't have to be the proxy.
Okay, cool. But the specific actor will be typed because it will only accept the specific authenticating authenticate user or something, right?
Yeah. Okay, so these were the behaviors and the tap behavior, right? Which again, is just putting something in front of your actor to check the message and signal before they go to the actual actor. And now, let me go quickly through how Akka typed actually solves some of the minor problems that we did experience in the past while writing Akka programs. So first thing, you probably are familiar with these two exceptions, right? First one mostly happen if your pattern matching is not exhaustive, and there are some options that go unhandled, right? So this may, for instance, happen. In case of any, that's a really broad word by saying you basically would have to have a catch-all clause in the end to avoid it. And the second one typically occurs to you if you use the ask pattern to retrieve messages from actors, and then it turns out, well, the message that you thought that you will receive was a Boolean, but actually what you received is an integer. Again, theoretically not Akka's fault, but it does happen. That happened to me a few times. So Akka Typed solved this by basically, well, introducing strict typing. So actors themselves have a strict type, and only messages of that type can be inserted into them, and so do the references. Actor ref is also parameterized by type. So if you want to respond to an actor ref, you also have its type known at the compile time, and you cannot respond with a different type than you are intended to. So the same thing happens with the ask pattern, which is also strongly typed. So all in all, you are 100% sure that the messages that you will receive, for instance, in the ask pattern, will be of the type that you think. And as for passing references, because I will also show an example of that in a minute, is basically actor refs are immutable and they are safe to pass around. So you can send them in, for instance, your command for the actor. You can say, okay, do this, and then respond to this actor ref with your result. And another problem which was I came across was basically who's the sender of the message, right? So in Akka, you usually had the sender method, which strictly returns the sender of the message being processed by the actor at a given moment of time. Now, if you do simple send respond, there's no problem in that. But it may so happen, and this is a often met scenario, that you have an actor that aggregates messages for which it asks other actors, right? So when you ask another actor, you essentially get a future of what you will be returned by the other actor, and then you will combine these futures and in the end return the result to to your sender. Thing is, if you call a sender like I did here, it may happen that at the time that this callback is executed, the actor is actually processing another message, right? Because this is asynchronous with regards to the actor. So the sender will return a reference not to the actor that sent the message to us originally, but actually to some other actor. And what will happen then? Well, for starters, you will not respond correctly, and then, well, it might be a pattern matching problem in that actor if it doesn't really account for that. Also, if it was an ask pattern, then again, class cast, so a lot of problems may arise. Now, of course, there were some methods for dealing with that in Akka, kind of hacks, right? But why do hacks if you can have the problem solved for you by Akka typed again? So in Akka typed, there is no sender, right? The behavior doesn't have a sender in it. How you respond to requests is basically in the request, you have to send the actor ref to which you should respond. So actor ref is strictly immutable, and no point in time will it point to a different actor than it was intended to. So you're 100% safe that you are responding to the correct sender here. And the third problem was that the one that I mentioned earlier. That's, well, in Akka it was kind of strenuous simulating changing behavior, the behavior that's dynamically changing. Now with all the behaviors having to return the behavior for the next step, it's easier and more natural to do that, right? To simulate systems that have evolving behavior, which are actually many systems. So now let me just start summing up slowly by talking a little bit about the prospects that Akka Types has in front of it. Well, the official LADMES statement goes like this, and about its future. And what's important here is when they say maturing such a profound change to the core concept of Akka will take a long time, and the plain Akka actor will not be deprecated or go away for any time soon. But what it means is basically there is, I guess, a plan to make Akka typed a core of Akka, but it's not going to happen now. It will happen in some remote future. On the upside, you actually have a degree of compatibility between Akka typed and standard Akka. You can use the standard untyped actor context to host typed actors, and I won't go into the specifics of that here because, well, time. But you have this blog post here, which is a Akka team blog post that explains in detail how you would do that, how you can take your current untyped application and basically put typed actors in there. Now, of course, and this actually enables doing all sorts of interactions between the two. So you can send messages, you can do supervision between them, right? It's pretty good. But what you need to remember is that compatibility on actors level doesn't mean that Akka typed is fully working with all the other modules, right? So for instance, if you take cluster, you can, I think, host typed actors in your Akka cluster, but if you decided to use a, say, cluster router pool in there, you cannot really start a cluster router pool of typed actors because it works on a standard actor. And for streams, I guess some operations are also not feasible, like I know, putting your typed actor as a receiver, I don't think that will work. So in summary, what's the main takeaway? I think the main takeaway from that presentation, I hope, is the understanding of the behavior-based philosophy of Akka type. And the other specifics are it brings type safety to Akka. It has this more functional programming like behavior-based philosophy. It does solve some of the known issues that arose in the past while programming Akka, like the sender thing or problems with the response message type. Yeah, and in some remote future, it will become the core of Akka. Well, surprisingly, we have some more time, so we have a lot of time for questions. Thank you for the attention. And do you have questions? Lots of them, probably. Yep.
Close enough to Mike, I will ask one more question. What about state? Because if you're changing API, kind of, maybe it's a good idea now to also pass a state of the actor explicitly in the behavior. So it's not only accepting context, it's not only accepting message, but also a state that's exactly like in Erlang or something.
Well, you mean like receiving that the actor would receive a state from...
From yourself, right? Because it's kind of looping.
Yeah, so how you would do that is you have this behavior, right? The method, so in the end of the method that Akka, so the actor immutable takes, you have to return a behavior. Actually, I could... I believe I've done that in my state machine example that I did.
Well, I don't know how to do it. Right? I'm just asking. Maybe it's a good time also to think about it. Maybe you need to respond with a tuple of behavior and the state or something, right?
No, so you don't need to do that. What you need to do is, if you have a method that defines the behavior, like here, right? I actually take some state that is passed around here. Here is just the reference to the client, right? But you can imagine that if you had some kind of state, right, you could essentially
the
pass
client is a state, okay, so, right. So this
it is a kind of state. Maybe it's not like a very typical one, but you could just pass the state between the methods defining different behaviors. Okay, that would be the idea of state management here.
Okay. What about Java? This API is also for Java or only for Scala?
Yeah, there is an API for Java. I didn't have the time to prepare the samples twofold, but there is a corresponding API for Java. And there is even for those who like the, let's say, old actor style, there's also the mutable behavior, which I always use actor immutable, but you could actually use actor immutable to write actors in kind of the same way that you did in the past, if that's what you want. But still type actors, right? Any other questions? Oh, that's sad. Okay, so thank you very much for listening.